Hello everybody and welcome to our video on maximum and minimum values. So alright, we're just going to jump straight into it. We're going to define a few things and then see what we can do with this. So definition, let C be a number in the domain D of a function f, then f of C is the absolute maximum value of f on D if f of C is greater than or equal to f of x for all x in D. So the key thing to understand here is that f of c is a y value, so there is a single such value when we talk about an absolute maximum. So for example, when we look at this curve to the left where I've labeled an absolute max and minimum, perhaps this curve kept going back up and maybe it hit the exact same height here. Then this is still the absolute maximum, because the absolute maximum is just referring to the y value for this function, so the highest y value. All right, and likewise, the absolute minimum value of f on D, f of c is the absolute minimum value of f on D if f of c is less than or equal to f of x for all x in D. So I think these definitions are pretty straightforward. It's a maximum if it's higher than the y values, or as big as or higher than the y values for every other point on the function. It's a minimum if the y value is smaller than or equal to all of the other y values on the function. Okay, you will often see the term global used interchangeably with absolute in this context. So someone might say global maximum or global minimum. That means exactly the same thing. All right, now let's go to our next definition. Let C be a number in the domain of f of x, then the number f of c is called a local maximum value of f if f of c is greater than or equal to f of x for all x in some open interval containing c. So for example, if I look over here to the right, let's call this point C. So this is called a local max if I can draw some small interval around C where this is the highest point on that interval. Likewise, this is called a local minimum. F of c is called a local minimum if f of c is less than or equal to f of x for all x on some open interval containing c. So notice the terminology is very careful here, on some open interval. Because I could always just draw this interval huge and oh, here's a giant interval. Well, it's not a local max anymore. Well, that's not correct. It only has to be true for some small enough interval. If you can draw any interval small enough such that that's the highest point on that interval, then it's a local minimum or maximum as such. Okay, so where was I? Oh, yeah. Let's move on to the extreme value theorem. So if f is continuous on a closed interval from a to b, then f attains an absolute maximum value, f of c, and an absolute minimum value, f of d, at some numbers c and d in the interval from a to b. So all this says is, if you've got a and b here, and you have some curve that's unbroken, it's continuous from one side to the other, there's got to be a highest point, and there's got to be a lowest point somewhere in the interval. That's it. Now, these conditions do matter a lot. If, for example, a function was not continuous, you might have this situation where the left side of the graph goes up to here, but it doesn't actually reach this value. So there is no maximum here, right? You can get arbitrarily close to the value, but it doesn't take that maximum value. Likewise, you might have continuity on an open interval, but not a closed. And if it's only continuous on an open interval, maybe this thing shoots up to infinity. And so here, there's no maximum, it can grow forever. And there's also no minimum because it can get close to, but will never reach this hole in the graph. Okay, so here's another theorem. So this one is simple to state, but a little tricky to prove. Not too tricky though. If f has a local maximum or minimum at c, and if f prime of c exists, then f prime of c equals 0. So we've got two conditions here. If there's a maximum or minimum at c and the derivative exists, then the derivative is 0. Now notice this theorem does not say the opposite. It doesn't say if f prime is 0, then it's a minimum or maximum. And in fact, I'll probably bring this example up again later. But if you look at y equals x cubed, right? This is a perfect example where the derivative of this function at 0 is 0, right? Y prime is 3x squared. And when I plug in x equals 0, I get 0. But even though that derivative is 0, this is not a maximum or minimum. So in other words, this theorem only goes one direction. If you already know it has a local max or minimum and the derivative exists, then the derivative must have been 0 there, but not the other way around. Okay, so with that out of the way, let's tackle the proof. So let's assume that f has a local maximum at c. Then f of c would be greater than or equal to f of c plus h for small enough h. And all that's saying is that if we take a look here, if I add a little bit, a distance h in either direction, if I go h in either direction, that value, the y value on the curve there, is still going to be smaller than f of c. So f of c, if f of c is greater than or equal to f of c plus h, then if I subtract this, I get f of c plus h minus f of c is less than or equal to 0. Now if we assume that h is positive, then we'd be dividing by a positive number, so we've got a negative divided by a positive, that's still less than or equal to 0. Well, negative or 0 divided by a positive number. So now if we take the limit as h approaches 0 from the right of this, well, what do we see? Well, this limit is 0. And since that limit is 0, right, what do we see? Well, since we know the derivative exists, it's been given that the derivative exists. That means the left-hand limit is the same as the right-hand limit. And so the actual derivative is just 0. Or I should say the actual derivative, let me rephrase that. This limit is less than or equal to 0, right? Because this thing is negative. And since this is less than or equal to 0, that says that f prime of c is less than or equal to 0. Okay, so now we look at the case when h is less than 0. So now we're looking at the left-hand limit. So if h was less than 0, the inequality would just flip around, and we'd do the same work, and we'd see that f prime of c was greater than or equal to 0. So again, both of these have to be true, right? We know that the left-hand limit and the right-hand limit have to be equal. I mentioned that a little earlier unintentionally, but the left and right-hand limit have to be equal. And so if I know that the derivative is less than or equal to 0, or greater than or equal to 0, there's only way both of those statements are true, and that's if the derivative is 0. All right, so I did already mention this a moment ago, but again, this is the example, x cubed is the example. The derivative being 0 does not imply it's a local maximum or minimum, but the other way around is true. If you have a local max or min, it does imply, if that derivative exists, that it's equal to 0. Okay, so let's tack another definition on here. A critical number of a function f is a number c in the domain of f such that either f prime of c equals 0 or f prime of c does not exist. So that's pretty straightforward. If the derivative is 0 or if the derivative doesn't exist, we call it a critical number. That x value is called a critical number. All right, so fact, if f has a local max or a local minimum at c, then c is a critical number of f. So this is just an evolution of that previous theorem, right? Because we know that if the derivative did exist, the derivative would be 0. So the only other possibility if you had a local maximum or minimum is that that derivative did not exist. All right, so those are the two possibilities here. So we're going to summarize all of these facts into a method, the closed interval method. To find the absolute maximum and minimum values of a continuous function f on a closed interval from a to b. First, find the values of f at the critical numbers in the interval from a to b. Second, find the values of f at the endpoints of the interval. And then third, the largest of these values is the absolute maximum, and the smallest is the absolute minimum. Okay, so let's go ahead and tackle this one. First, we'll take the derivative. That's 3x squared plus 12x minus 15. Okay, so in order to find out where this thing is equal to 0, I'm going to have to factor it. So I'm going to multiply 3 times negative 15. It's negative 45. And I want factors of negative 45 that add up to 12. A positive 15 and a negative 3 would do the trick. So I'm going to rewrite this derivative as 3x squared plus 15x minus 3x minus 15. So at the start here, we'll factor out a 3x from this pair times x plus 5. And we'll factor out a negative 3 here, negative 3 times x plus 5. All right, so now we've grouped these into 3x times x plus 5 minus 3 times x plus 5. So grouping them together, we get 3x minus 3 times x plus 5. So then f prime of x equals 0 when x equals 1 or x equals negative 5. So I'm skipping that step, but of course, you just find that by setting each factor equal to 0. 3x minus 3 equal to 0. Solve for x, you get x equals 1. X plus 5 equal to 0. Solve for x, and you get negative 5. So those are our critical numbers. But we should always think about where the derivative might not exist. But of course, this function is differentiable everywhere. It's a polynomial. So we'll just note that this exists everywhere. So these are my only critical numbers. All right, let's go ahead and take a look at another example here. Find the critical numbers of g of t equal to the absolute value of 3t minus 4. So remember, absolute value is a piecewise function. So 3t minus 4 when 3t minus 4 is positive or 0. But that's the same thing as saying t is greater than or equal to 4/3. And it's 3t, it's the negative of 3t minus 4 when 3t minus 4 is negative, or when t is less than 4/3. So this is clearly differentiable for t greater than 4/3 and t less than 4/3 because those are just polynomial functions. But g prime of 4/3 does not exist. And we've shown before that the derivative of an absolute value doesn't exist when the absolute value is 0. So that's what we're saying here, right? This absolute value, you get 0 for 4/3, and we know that the derivative of the absolute value doesn't exist at its 0. So this doesn't exist, so x, or t, I should say, equal to 4/3 is the critical number. All right, let's go ahead and move along. Okay, so now we're going to start applying this idea, and we're going to find the absolute minimum and maximum of f of x equal to x cubed minus 6x squared plus 5 on the interval from -3 to 5. Okay, so let's start by taking the derivative. We get 3x squared minus 12x. Derivative of 5 is 0. And now I want to be able to check where is this thing 0. So I'm going to factor out 3x. I get left with x minus 4. So this derivative is 0 when x equals 0 or x equals 4. Right? That's when this factor is 0, x is 0. This factor is 0, x is 4. So now we just need to check the value of f at these critical points and at the endpoints. That's what the closed interval method tells us. Just check the endpoints, check the critical points, and then you're good. So let's evaluate f at -3. So we get -3 cubed minus 6 times -3 squared plus 5. -3 cubed is -27. This is going to be -6 times 9. That's -54 plus 5. This is -81 plus 5. That's going to be -76. Okay, so the next x value is 0. And f of 0 is easy. Plug in 0, you get 5. And then we have f of 4. Okay, what's f of 4? We get 4 cubed minus 6 times 4 squared plus 5. That's 64 minus, so this is 16 times 6. So that's going to be, so 16 times 5 is 80, so 96. This is going to be 64 minus 96 plus 5. This would be a -32 plus 5. That would be -27. And finally, we'll check f of 5. That's 5 cubed minus 6 times 5 squared plus 5. That's 125 minus 25 times 6, which is 150, plus 5. It's -25 plus 5, that's -20. Okay, so the smallest of these values is the absolute minimum. So this is the absolute minimum. And the largest is the absolute maximum. And that's it. That's the whole process. So let's go ahead and take a look at another problem. Find the absolute minimum and maximum of f of x equals x squared minus 1 cubed on the interval from -1 to 2. Okay, we'll start by finding the derivative, f prime of x equals, and we've got to apply the chain rule here. We get 3x squared minus 1 squared times the derivative of the inner, which is just 2x. All right, so remember this is your u. Take the derivative of u cubed. It's 3u squared times du dx. Okay, rewriting this slightly. This is 6x, 3 times 2x. And then inside this square, I'm going to factor the x squared minus 1 into x minus 1 times x plus 1 squared. So this is 6x times x minus 1 squared times x plus 1 squared. That makes it very easy to find my critical numbers here. F prime of x equals 0 when x equals 0, x equals 1, and x equals -1, right? When this factor is 0, this factor is 0, or this factor is 0. Okay, and now our interval is from -1 to 2. That's kind of nice because there's an overlap here. Another thing to keep in mind that might happen, it's not going to happen on these examples, but another thing that might happen is that since you're only looking at the interval from -1 to 2, it's entirely possible that one of the critical values for your function is not inside your restricted interval, in which case, when you find that critical number, you would actually ignore it because it's not in the interval you're concerned with, so you just would kind of toss it out. But that's not a problem here. Okay, so now let's go ahead and check the function at all of the appropriate values. We'll start with the smallest, f of -1. That's going to give me 1 minus 1 cubed, that's 0 cubed, that's 0. And now we've got 0 next. F of 0 is 0 minus 1, that's -1 cubed, that's -1. We'll check 1, we get 1 minus 1, that's 0 cubed. And f of 2. That's 4 minus 1, that's 3 cubed, which is 27. So 27 is the absolute maximum, and -1 is the absolute minimum. All right, that's it for that example. Let's go ahead and move along. Okay, find the absolute minimum and maximum of f of x equal to ln of x squared plus x plus 1 on the interval from -1 to 1. So let's start out by taking our derivative. Get 1 over x squared plus x plus 1 times so this is my u. So this is my derivative with respect to u, 1 over u, times du dx, which is 2x plus 1. And so we need to check when is f prime of x equal to 0. Well, that's when 2x plus 1 equals 0. So that's x equal to -1/2. Now, one thing that I skipped on the last couple, I didn't check if the derivative didn't exist, but this is a polynomial. The derivative exists everywhere. This one is also a polynomial. That derivative exists everywhere. Now here, we have a denominator, x squared plus 1, or plus x plus 1. So we gotta go back to checking, where does the derivative not exist? Well, that would be if x squared plus x plus 1 equaled 0. Well, I could try to factor this, but it won't work. What I could do is check the quadratic formula. So -b plus or minus square root of b squared minus 4 times a times c, all over 2 times a. And what do we see? This thing inside here, we call this the discriminant, as a reminder. And that's because it discriminates between the types of solutions that you will have. Either 2 solutions to a quadratic, 1 solution, or no solution. In the case of this, we have a negative value inside that square root. Can't take the negative square root number, at least not in the real number system. So we would say that there is no solution there, and hence there is no place where this does not exist. So we'd say f prime exists everywhere. However, when you see a denominator that could possibly be 0, you definitely want to double check that so you don't miss those critical numbers. Okay, now with that out of the way, let's tackle the rest of this. So we've got one critical number, x equal to -1/2, and we've got to check our endpoints. So I check -1, I get the natural log of 1 plus 1 plus 1. That's ln, 1 minus 1 plus 1. Oops. That's ln of 1. And ln of 1 is 0. And now I'll check 1/2. That's -1/2. Let's just rewrite that. F of -1/2. That's the natural log of 1/4 plus 1 minus 1/2 minus 1/2 plus 1. That's 1/4 minus 2/4 plus 4/4. That's 3/4. That's ln of 3/4. Now we check f of 1, and that's going to be ln of 3. So, how do I got to figure out what my absolute maximum minimum is? You could plug these into a calculator, but that's not really necessary here because ln of 3/4 is less than ln of 1, and ln of 1 is 0, right? We know that the natural log, the graph looks like this. So that tells us that this is negative. So in other words, ln of 3/4 is our absolute minimum. And ln of 3, which is bigger than 1, is the absolute maximum. Okay. Well, that was our last example for maximum and minimum values. Thank you for watching.